Thank you so much, Kim and Vasily, for inviting me here. I'm delighted to be here and honor Professor Louis Kauffman 80th birthday. So today I'm going to talk about the Kauffman bracket Skein modules of length spaces and some other interesting cases related to the length spaces. And I'm going to use an algebraic approach via braids. So it's you can call it like a braid theoretic approach towards the Kauffman bracket Skein module of three manifolds in general, but I will focus to length spaces today. So Skein modules were introduced by Skein modules were introduced by Psititsky and Turaev back in late 80s, early 90s. And they are quotients of free modules over isotopic classes of links in three manifolds, where we consider some properly chosen local relations, Skein relations, that characterize a specific polynomial. And they have become extremely important because, first of all, they unify, let's say, polynomial invariants such as the Jones, Humphrey, even the Alexander. And of course, they encode topological properties of the three manifolds and their fundamental groups, of course. For example, non-separating spheres can be detected by torsion in Skein modules, as we will see. And they also arise naturally in topological in quantum topology and mathematical physics in general. So let's introduce what Skein modules are. Let's have the definition. So we have a three manifold, an oriented three manifold M, any three manifold. All right, we consider R to be a ring with unit. And we take the set of isotopic classes of framed links. In this talk today, I'm going to only consider framed links since we are talking about Kauffman bracket Skein modules. But one can consider isotopic classes of oriented links and compute the Humphrey Skein module of three manifolds. And then the Kauffman bracket Skein module is defined as this quotient that you see here, where we have the free R module, let's say, generated by the isotopic classes of framed links, modulo some Skein relations, the classical Skein relations that characterize the Kauffman bracket polynomial, where here you can see this is the relation where L infinity, and L0 are depicted in this figure. They are identical links everywhere except from one specific crossing that they look like this. All right, so in the language of Skein modules, the Kauffman bracket Skein module of S3 is freely generated by the unknot. Why is that? So assume that you have a knot diagram, right? You have a knot in S3, you consider a knot diagram, and you start using the Skein relation where you eliminate a crossing each and every time. You end up having a bunch of unknots in the end. For the case of the solid torus, I think Kidwell and Hoste in late 80s, early 90s, they proved that the Kauffman bracket Skein module of the solid torus is generated by elements of this form, x to the power of something, right? Where you see here we have the affine knot, and here we have what I call essential unknots, right? In this talk, I will call them essential unknots, where for Kidwell and Hoste, the solid torus was considered to be like annulus cross interval. All right, and we see the basis here. And of course, we understand here also that we have no crossings, right? So imagine that you have a diagram on the annulus, a knot diagram on the annulus, and you eliminate the crossings using the same Skein relation that characterizes the Kauffman bracket polynomial. You end up into a bunch of these elements. All right, so this is the basis of the Kauffman bracket Skein module of the solid torus. Now, what I'm going to do today, I'm going to present the algebraic approach, and I'm going to tell you a little bit roughly the outline of this approach, how we use it and why we are using it. So the main idea is the following. We have a three manifold. You can consider any three manifold you like, CCO three manifold. Then we find a way to represent knots and links that live in this three manifold as a special type, a special kind of knots that live in S3. So we use that using what I will call later on the mixed links. Okay, and this you can do for any three manifold. I will be using Kirby-like diagrams for this. So mixed links are like Kirby-like diagrams where you also have the knot that lives in the three manifold, and you also have a description of that three manifold via a specific knot and its surgery. Then, after we have this type of knot in S3, of course, we translate isotopy using using the analog of Reidemeister theorem. We analyze isotopy moves for knots and links that live in that three manifold. Remember what I said? I'm going to use braids, right? So I'm going to use an algebraic approach. So the next step would be to establish the analog of Alexander's theorem and have what we call mixed braids, which is a special kind of braid that lives in S3, but it's a nice way to visualize these braids that live in the three manifold. And of course, the next step, which is logical and natural, arises is like to establish the analog of the Markov theorem and have isotopy translated on the level of braids. All right, so we have the braid equivalence for this. Then these mixed braids would form groups, and we are interested in the algebraic structures that we can have. For example, we already know that the Home-Flipped polynomial can be obtained through a Markov trace, right, from the Hecke algebras. Now, if you consider the Hecke algebras of type A and you find a Markov trace, you construct, and the Ocneanu trace, you get the Home-Flipp polynomial for knots and links that live in S3. But if you consider the generalized Hecke algebra of type B, you do the same thing, but now you consider knots that live in the solid torus. And of course, you can continue like that, but there are many open questions now. For example, the two-boundary Hecke algebra, I don't believe that we have an Ocneanu trace, a Markov trace here. Not yet, I guess. Then you can do the same for the Kauffman bracket using the temporal Lib algebras. Again, type A corresponds to polynomial invariance for knots and links in S3, generalized type B for the solid torus, and it goes on like this. And of course, we also have the BMW algebras, where you can recover, let's say, the two-variable Kauffman polynomial, and the Alexander polynomial, and many others. And of course, using these structures and using a Markov trace, we are trying to normalize this trace and create invariants for knots and links in these three manifolds. And we will show that this is equivalent in computing the Skein module of a three manifold. All right, so this is roughly the outline of today's talk. This is roughly the idea, and I will focus on how to evaluate, how to compute the Kauffman bracket Skein module of the length spaces. I will emphasize on the case LP1 because it's easy to visualize and see, and easier for me to explain. But these methods also apply for the length spaces LPQ. I will also discuss that. And also for S1 cross S2, where we will see that we have there we also have torsion, and it's the first time that torsion is captured using the braid method, because all the three manifolds I managed to compute the Kauffman or the Home-Flipp Skein module of these three manifolds, they didn't have torsion so far. So S1 cross S2 is the first one that I proved that using the braid approach we can capture torsion, and I will explain how and how to describe it also. All right, so let's start by representing knots and seeing how we can represent knots that live in length spaces as knots that live in S3. So we start by recalling a little bit the construction of the length spaces. For example, we start by, for this talk, we will consider the length spaces to be obtained from S3 by rational surgery with coefficient P over Q along the unknot, which means that we take a solid torus, right? We take the tubular neighborhood of the unknot, we drill it out, and then we put it back, but now we attach it to the remaining solid torus according to a PQ homomorphism on their boundary. Which means that we understand immediately that the intermediate step before one obtains the length space is the solid torus. And this is going to be very important because the Kauffman bracket Skein module of the solid torus is very crucial to understand how the braid approach works here in order to be able to extend it for the case of length spaces. So let's assume that we have a knot, as we can see here, a knot in the solid torus. I hope you can see my mouse, the pointer of my mouse. So I have here a diagram, a knot diagram in the solid, a knot in the solid torus. And I will visualize that as a mixed link in S3. What is a mixed link? So I am considering this black curve to be fixed, all right, and representing the complementary solid torus. All right, so mixed links consist of, they have two parts, the fixed part that represents the three manifold and the moving part that represents the link that lives in that three manifold. So here is a mixed link that represents a link in the solid torus. Of course, this, as I said before, this is the intermediate step before you go to the lens space. So in order to go to the lens space, you also have to consider the surgery description of the lens space, which we will soon see how we can translate that for mixed links, for the case of mixed links. So we have mixed links and we visualize knots and links that live in lens spaces or in the solid torus if you prefer for to start with, and we consider mixed links to represent them, to visualize them. So a mixed link has two components. One is the unknot, which is fixed and represents the complementary solid torus, and the other one, the gray part, is the knot that lives in the solid torus, and it's the moving part, which means that we have the Reidemeister moves, the regular Reidemeister moves for this part of the mixed link. So as I mentioned, we have the Reidemeister theorem, the analog of the Reidemeister theorem. So when do we call two knots and links, two links, let's say isotopic in the solid torus? So we consider diagrams, mixed link diagrams, and if they differ by a finite sequence of these moves that you see here, we consider them isotopic. So let's review a little bit the moves. Here we can see planar isotopy, we can see the delta move, the classical Reidemeister 1 move, Reidemeister 2 and Reidemeister 3 moves, but we also need some extra moves to describe isotopy in the solid torus, sorry. And these are what we call the mixed Reidemeister moves. And we have two types. The first type is the mixed Reidemeister 2 move, which resembles the Reidemeister 2 move, but it involves both the two components of the mixed link, the fixed unknotted part, right? The black strand that you see here, and the gray strand that you see here over there, which is the moving part of the knot. So the moving strand can go below, right, or above, of course, the fixed strand, and it can be pushed back. And we also have the analog of the Reidemeister 3 move, where we can see that we have one fixed strand, right? And we have two moving strands and a crossing that can cross to the other side of the fixed strand, all right? Of course, not always. For example, if that was an overcrossing and that was an undercrossing, this is not possible. So this is the analog of the Reidemeister 3. And these moves suffice to describe isotopy for knots and links in solid torus, or if you like, for mixed links in S3 that represent links in the solid torus. All right, so moving on now, we need to go and understand a little bit isotopy in lens spaces. So we have the solid torus, which was the intermediate step, and in order to go to the lens space, we have to add one more move, which corresponds to the surgery description of the lens space. And this move is called a band move, which, if I recall correctly, it also appears in Psititsky's and Hostes' paper on their computation of the Kauffman bracket Skein module of the lens space using a completely different approach. All right, so what is this band move? Here we have to explain a little bit in detail how it works because it's very interesting. So we have two different cases depending on the orientation. So we can see here that the moving strand approaches the fixed strand, and if the orientations disagree, then this strand, the moving strand, is replaced by a P1 torus knot in this particular case because I'm showing you the LP1 case. So this strand is replaced by a strand that wraps around the surgery curve P times. And this comes from the fact that the P1 torus knot bounds a disc in LP1. And similarly, a PQ torus knot bounds a disc in LPQ. And we have another type, which is the type Vita band move, where you can see here initially the orientations agree, but after the performance, which is similar to what I explained before, the orientations disagree. The orientation of the moving part and the fixed strand. And here the orientations initially disagreed, but after the performance, the orientations agreed. So we have two types of band moves, and of course, you can imagine, it worked. You can see how it works for the case of a PQ, LPQ, right? So Q strands appear wrapping around the surgery curve P times. All right, I will explain this extra crossing in a minute because this is very important for the braid approach. But these are the two types. This is the type alpha, the type A, and this is the type Vita, the type B. We call this braid band move later on because it works on the braid level. Now, with Labropoulou in 2015, with Professor Labropoulou, we proved that one of these two moves suffice to translate isotopy for links in a three manifold. Be careful, by a three manifold, of course, I'm focusing in length spaces for these moves that I show you here. But in the paper, we made it more general for any three manifold. You have the two types of band moves depending on the node that you are using and the P over Q coefficient that you're using for the surgery. And we proved that only one move is suffice in order to translate isotopy. And how did we do that? We proved that one move is a result of the other move plus some classical Reidemeister moves, or if you want isotopy in the complement. So both moves would do. One has to choose whether he wants to use this one or this one. And in this talk, if I have the time, I will use both. So when I do the algebraic approach, the braid approach, I'm going to be using this move, as I will explain later. And when I'm using a diagrammatic approach via braids, I'm going to be using this move, and I will show you the pros and cons of each one later. So we have isotopy for mixed link isotopy for nodes that for mixed links that represent links in length spaces. So we have the classical Reidemeister moves for the moving part. We have the mixed Reidemeister moves for the moving part and the fixed part, as we said before. And we also have the band moves that involve, that actually correspond to the surgery description of the three manifold that we have. All right. Now, moving on. Now we want to go and understand a little bit how one can use the braid approach. So first, we have to understand how to obtain a braid from a mixed link. So what is a mixed braid? In other words, it's nothing but a braid where it's fixed strand, which without loss of generality, we will always assume to be the first strand of the mixed braid. It represents the complementary solid torus. All right, and the moving subbraid corresponds to the moving part of the mixed link, which is nothing but the link in the length space. All right, and so what is a mixed braid? Is nothing but the braid presentation of the mixed link. And of course, we need now, as I mentioned in the outline of today's talk, we need the analog of Alexander's theorem in order to be able to proceed and go towards the analog of Markov's theorem. All right. So if I remember correctly, Labropoulou proved that a mixed link diagram can always be turned into a mixed braid with isotopic closure. And if I remember correctly, it was in her PhD thesis and her work with Rourke. And by closure, we mean the standard closure that as we know it for standard braids and standard knots. All right, so we have the analog of the Alexander theorem, which is very important. And now we try to see whether we have an algebraic structure, whether we have a group structure. And actually we do, because the braids that actually are related to the solid torus, they form groups. And these are the Artin braid groups of type B that we will denote from now on as B1N, one to denote the one fixed strand, which is the first strand, and N moving strands that follow after that. And we also have a presentation of that Artin braid group of type B. And here are the generators, right? So we have the sigmas, the classical generators from the braid group, the classical braid group, and we also have an extra generator, T, the loop generator, as you can see here. And this is going to be extremely important. So we denote it by T. And of course, the presentation has the classical relations of the braid group plus relations of the interaction between T and sigma. So we can see that if sigma is far away, T and sigma commute. If I is greater than 1. And if I is equal to 1, we have this relation here, sigma 1 T equals T sigma 1 T sigma 1. So that's the presentation of the braid group, of the Artin braid group of type B, which corresponds to mixed braids in the solid torus. All right. And from that, we're going to see how we can get the Hecke algebra and follow Jones's original approach and obtain Markov trace and polynomial invariant for knots and links in the solid torus first, right? For this, using the mixed braid approach. All right. So the Markov theorem, which is the analog of the Markov theorem, which is extremely important for us here, says the following, that if you have two links in the solid torus and you get two corresponding mixed braids of theirs that differ by a finite sequence of these moves, right? If you have that, then the two links are isotopic. So what are the moves? We have the classical conjugation and stabilization moves as in the classical case of the braids in S3. And we also have an extra move, which is the loop conjugation. So which is, I think it's very natural, right? So if you have a loop here, a loop generator here, a T, this loop via conjugation can be gone here, right? Below, from up, down. So this is the loop conjugation and this is its algebraic expression. Now, if one wants to establish the analog of Markov theorem for knots and links in length spaces, right, for mixed braids that correspond to braids in length spaces, what we have to also do is involve the band move. So now we need to translate the band move on the level of mixed braids. So we define what we call a braid band move. So what is a braid band move? A braid band move is a move between two braids, right, two mixed braids, that is a band move in their closure. All right, so that would be a band move. And if you open this up, it will look, and bring it to a braid form, it will look like this. So let's see, as a fixed strand a moving strand approaches the fixed strand, it's been replaced by a new strand that wraps around the surgery curve p times. I am showing you the P1 case, right? The LP1, the length space LP1, wrapping around it p times, respecting the same crossings that the fixed strand had with the moving strands. You can see here it goes below and above this strand as here. And then we have an extra crossing, a sigma 1, as we can see here. And why do we have that? Remember that the band move, when the orientations agreed in the beginning, if you perform a band move, the orientations would disagree. So you are not on the level of braids anymore. So what we do a type alpha band move, where originally the orientations disagree, but after the performance, the orientations agree. And how do we do that? Since for braids, we have a natural top to bottom orientation, when the moving strand goes down, we perform a Reidemeister 1 move, positive or negative, in the beginning. So now we are not on the level of braids. That's the intermediate step. And then now that the orientations disagree, we perform a type alpha band move and the orientations now agree. And depending on the Reidemeister move that we perform in the beginning, the kink, if it's positive or negative, we have a crossing here, a positive or a negative crossing in the end. So if one has to translate algebraically this band move, this braid band move, would say that if you have a braid B, whatever, and you perform a band move, then this is replaced by T to the power of P, right? The loop generator to the power of P, because it wraps around the surgery curve P times, followed by the braid, exactly the same words, but all the indices shifted by 1. I denote this by B plus, right? And in the end, I have a sigma 1 generator to the power of plus or negative 1, depending on the kink that I perform, positive or negative Reidemeister move. All right. And of course, we can do that for any. I'm just showing you some examples here. This is for the 3-2, right? The 3-2 for L32. So you have three extra strands appearing, wrapping around the surgery curve twice. That's the 3-2. So you create a 3-2 torus knot. And you can see here the algebraic approach where I perform a PQ braid band move. So Q new strands appear, wrapping around the surgery curve P times. For this case, I think this is not a mistake. I put the sigma 1 here as a sigma q. We proved in with Labropool in 2015 that it doesn't matter. This is just a choice. So we would prefer to have it as sigma 1 always, so that it is easy to describe algebraically. And we will be consistent also. All right. And of course, you can see that I will be using this for the diagrammatic approach, and this is not a braid anymore, right? This is the type Vita band move, and we are not on the level of braids anymore. We will discuss that too if we have the time. All right, so we have the analog of Markov theorem for length spaces in LPQ. Here you can see LP1, we have the classical conjugation and stabilization for the moving part. We have the loop conjugation, which corresponds to the solid torus, if you remember. And we also add this braid band move. Here you can see for P1, LP1. And of course, you can make it for PQ, where you add this move instead of the P1. So we have the analog of the Markov theorem for length spaces, LPQ. Now, a very important observation, let's go back to the computation of the Kauffman bracket Skein module of the lens spaces. One extremely important observation here is that we can use the Kauffman bracket Skein module of the solid torus, right, and study the relations that come from the band moves or the breakband moves, if you want, study these relations and how these relations affect the Skein module, the basis of the Skein module of the solid torus. And this observation was made by Psititsky and Hoste in their famous paper where they computed the Kauffman bracket Skein module of the lens spaces. So we understand immediately that the solid torus is extremely important. And let's see what we have. Let's review a little bit what we have. I will be a little bit fast because I see my time, I'm running out of time. So we have mixed links in S3 that represent links in the solid torus. We have isotopy, right? We have the analog of Alexander's theorem, and we have Markov. And then we have the braid, the Artin braid groups of type B that correspond to these mixed braids for the solid torus. Then, if you take this algebra modulo, this quadratic relation sigma I square minus q minus 1 sigma I minus q, one gets the generalized Hecke algebra of type B, which is of infinite dimension because T, the loop generator, does not satisfy any polynomial relation. And from this algebra, Labropoulou constructed an Ocneanus trace, which is very similar to the classical trace of Ocneanu, right? You can see the first three rules are the same, but this fourth rule makes the huge difference, where you have elements of this form, right, that we call Ti prime, right, behaving like that under the trace. And this Sk is the unknown, if you like, or the parameter that corresponds to Kidwell's and Hoste basis for the essential unknowns, if you remember. And from that, if you just normalize it, you get the two-variable Jones polynomial, or if you want the Humphrey polynomial for knots and links in lens spaces. So I followed the same idea as Jones. I took this, before that. And this is the invariant that Labropoulou created for knots and links in the solid torus, which corresponds to the Humphrey. All right. And also this invariant recovers the Humphrey-Skein module of the solid torus. So it's also very important. Now, I use a completely different presentation for that, where I'm using a different quadratic relation for the Hecke algebra, because it makes a little bit the calculations simpler. And what I did was the following. I followed Jones's approach. So I took the generalized Hecke algebra of type B, from which one can recover the Humphrey-Skein module of the solid torus, and I took the quotient of that over the ideal generated by elements of this form, which is in the classical case, if you had the Hecke algebra here of type A, you would get the temporal leap of type A. Now, in this generalized temporal leap algebra of type B that I defined, I managed to prove that the trace that Labropoulou constructed for the generalized Hecke algebra of type B passes through to the Hecke algebra, to the temporal leap algebra, right? And this happens when the trace parameter takes this value. All right. And then using this, I obtained, using this Ocneanu trace, I obtained the Jones polynomial, which is, let's say, the universal Kauffman bracket type invariant for knots and links in the solid torus, which is very important because it will be my, let's say, the starting point for generalizing this invariant for knots and links that live in lens spaces. All right, and I prove that this invariant recovers the Kauffman bracket Skein module of the solid torus. How? By assigning to elements in the basis of the Kauffman bracket Skein module of the solid torus different values. So it actually recovers it, which is very, very, very crucial, because I have this universal bracket type, and from that, if I try now to understand how the breakband moves affect this invariant, I can generalize it and I can extend it to an invariant for knots and links in lens spaces. And that's actually what we did. So I had to solve an infinite system of equations coming from the breakband moves. And that was tricky, I have to admit. So, of course, we can have the combinatorial approach of Kauffman, where here you see the classical approach for the Kauffman bracket polynomial for knots and links in S3, right? And if one wants to make it, to extend it, let's say, for knots and links in the solid torus, one has to just add these two rules. So I added these two rules, which are very similar to the trace rule of Lapropoulou, if you remember, and I obtained the Kauffman bracket for knots and links in the solid torus. And of course, using the normalized version with a Wright also and a change of variable, one can obtain the Jones polynomial. So that's the combinatorial approach, just a parenthesis towards that. And of course, another parenthesis, one can do exactly the same for notoids that live in the solid torus. I think, or I hope that Professor Dr. Sonia Mahmoudi talked about it. We are working on that, right? So we have notoids, which are like a special type of knots. We consider the diagrams, right? It's a diagrammatic theory. We consider the diagrams on the annulus and their lift on the annulus cross interval. So we have notoids in the solid torus, right? We have isotopy. I will not bore you with that. And some extra allowed moves, non-forbidden moves or whatever, and one can use exactly the same rules that I showed you before to have the analog of the Kauffman bracket for notoids that live in the annulus. All right, that was a parenthesis. I stop and I continue now with the Kauffman bracket Skein module of the length space. So, and I say I have 10, 15 minutes. So, as I said before, we have an invariant, which is a universal type. It recovers the Kauffman bracket Skein module of the solid torus, and we want to extend it to an invariant that captures the Kauffman bracket Skein module of the length spaces. How do we do that? We analyze the relations that come from braidband moves. All right, and that gives an infinite system of equations that one has to solve. And now we need to simplify the system as much as possible. And what we observe immediately, we observe that the Kidwell-Hoste basis, which is depicted here, right? We see that it has no crossing, which is as expected, because remember the Kauffman bracket relations eliminate all the crossings. But on the level of mixed braids, we see crossings, right? Which is not natural for the Kauffman bracket because one can apply the Skein relation and kill all the crossings. So because we change our view, we create crossings, right? So we immediately saw that there should be a different basis and easier for us, easier basis to use for computing the Kauffman bracket Skein module of the length space. And of course, we got this beautiful basis, t to the power of n. So one generator to the power of n, right? Let's say the wrapping number. And we proved first that this set here forms a basis for the Kauffman bracket Skein module. What is very interesting is that on the left here, you see the Kidwell-Hoste basis, no crossings. On the level of mixed braids, you see a lot of crossings, which is not natural for the Kauffman bracket. And then you have a new basis that has no crossing, right? But when you translate it again back to the Kidwell-Hoste representation of knots and links in the solid torus, you see that there are crossings. So for us, this is a very natural basis, but for the diagrammatic approach using the annulus and annulus cross interval for knots in the solid torus, this is more appropriate. So I find it fascinating, this part, because using this, the system of equation that one has to solve in order to generalize our invariant V for knots and links in the solid torus to an invariant for knots and links in length space becomes easier. All right. And I also have a different motivation. What was our initial motivation? But I will skip that for now. That I think that this is enough to give you an idea why we needed this new basis. Number one, as I said before, because there are no crossings, which makes perfect sense. But number two, which is even more important, is because of the system that one has to solve becomes quite simple. All right. So I move on to. Okay, and I also did the same for the Kauffman bracket Skein module of the solid torus, but dealing with notoids here. And now I want to show you a little bit the idea behind the Kauffman bracket Skein module of the length spaces and how I solved the infinite system. So recall that we have an invariant, right? And we have a Markov trace. And this is the extra rule that the Ocneanu trace has to satisfy in order to have an Ocneanu trace for knots and links in the solid torus, right? For the generalized Hicke algebra of type P. And you see here the Ti prime. These are very important. So these SKs are going to be the unknowns of the system. All right. So how does this work? We start by taking elements in a basis of the solid torus, of the Kauffman bracket Skein module of the solid torus. We prefer the new basis, t to the power of n. Okay, and then what do? We perform braidband moves. All right, positive and negative. Remember, with the positive and the negative kink, unfortunately, we require both. So for each element in the basis, we have two relations, two equations for each element. So this is an infinite system. And step one, I proved that this system, and that was not very difficult to prove, that this system splits into subsystems, and each subsystem, every element of this form, where k is a natural number, every element of this form where the index exceeds p can be written as a combination of elements where the index does not exceed p, right? But it could be, unfortunately, negative index. By negative index, we mean instead of a positive loop, a negative loop. All right, so instead of going above the fixed strand and then below, first it goes below and then above. But of course, greater than negative p. Then I prove that the negative indices can be written again as a sum, as a combination of elements. Here I forgot to put the coefficients, so there are coefficients here. So to translate them uh, into positive indices, and then finally prove linear independence. And what I obtained is very similar to Kidwell and Hoste, Psititsky and Hoste result. Not the same basis, though, right? But very similar, because you can see t to the power of n, where n lives in this set here, right? It forms a basis for the Kauffman bracket Skein module of the length spaces LP1. Same for LPQ. There was no difference. The system was a little bit more challenging because of the more challenging Kauffman bracket, braidband move. The relations were a little bit more challenging to describe, but exactly the same basis we got for any P and Q. All right, and here are some examples with computations. I'm going to skip that because I want to show you a little bit S1 cross S2. I think this is very interesting and important. So this is a special case of length space, right? L01. So in other words, you have the unknot and you perform a zero surgery on the unknot in S3. Or a nice way of visualizing S1 cross S2 is by having like a 3-ball and S2 glued out, right? And then, not glued out, wrapped out, and then glue the boundaries of these two. And the topology, this space is very interesting because one can easily see that if you start with a knot that lives in S1 cross S2, you can use this S2 here to unknot this knot. Right, as you can see, like you can take that to the other side, and once it's on the other side, this is just unknotted. Of course, if I zoom in, you will see here that it has a framing. All right, and this is known as the Dirac trick or the Dirac belt for unknotting a knot in S1 cross S2. So this was very interesting to me to see whether the braid approach could work, and it did. Of course, we have some positive and some negative results. Um, as always, we first translate the band moves, right, to for the level of on the level of braids. So we have the braid band moves, and here what is interesting is the following: we are still using Psititsky's result, where it says that in order to compute the Kauffman bracket Skein module of S1 cross S2, you need to consider any basis of the solid torus, of the Kauffman bracket Skein module of the solid torus, and analyze relations that come from the braidband moves, positive and negative, depending on the kick, as you can see here, right? So extremely important was, and the key idea was the following here. I said and here you can see a braidband move, how it looks for the case of S1 cross S2. And here I said by classical general arguments, instead of computing this, you can first analyze the effect of a negative braidband move, and to the resulting set, you can analyze the effect of a positive braidband move. All right, and then you have the Kauffman bracket Skein module of S1 cross S2. So that was the key idea behind this, and it worked as follows. So we first study the negative braidband moves, right? The effect of the negative braidband moves on the elements of our new basis of the solid torus. And what we saw is the following. If you start with a trivial knot and you perform a negative braidband move, the equation is trivial. 1 is equal to 1. If you start with one looping generator and you perform a braidband move, a negative braidband move, then you get S1 equal to S1, which again is nothing. So in other words, these are, for me right now, the way I see it, these are free parts, right, of this Skein module. Oops, sorry. And then for n greater than or equal to 2, I prove that anything, right, for n greater than or equal to 2, any t to the power of 2, 3, 4, or whatever, can be written as a sum, right, of these two, with some coefficients that I also here omit. Okay, and then I say, all right, so we have the free part, which is generated so far by 1 and t, the affine unknot and one essential unknot, and the rest are generated by these two. And then I take these two elements and I try to see the effect of a positive band move. And again, I see that for the affine unknot, the unknot, there is nothing. So this is the free part of the Kauffman bracket Skein module of S1 cross S2. But for the loop generator, I've found that it is generates torsion. So this is the torsion part. And I think this was the most important idea. Unfortunately now, using the braid approach and the Markov trace on the generalized temper-Lib algebra of type B, I wasn't able to come up with a closed formula for the torsion. I was able to understand that the free part is generated by the anode and the rest is torsion, but I wasn't able to have a closed formula for that, which I did using the mixed braid approach via using diagrams of mixed braids, but not algebras. All right, using that, which is similar to Psititsky and Hoste, I got a similar result, not the same, but a similar result like this. I think that I will. I don't know if I have time. Kim, do I have more time or like 40 minutes?
Actually, the
Okay, good. So I stop by saying that we have some open questions that are very important, and I am working on that. There is a lot to be done using Hecke algebras, temporal-Lib algebras, defining Markov traces in order to construct invariants for knots and links in other three manifolds in general. And I stop here. Thank you so much. Oops.
and thank you, Raj, for interesting talk. Let me finish